Hello. Now we will study the moment of inertia for hollow sphere. So this is our hollow sphere. So obviously inside there is nothing and outside there is nothing. So this width which I am showing right now is very, very small. So this thickness is very small. This one. Okay, so we want to calculate the moment of inertia for this. Now we have the formulas, where we have certain formulas to calculate the moment of inertia. We have the moment of inertia, we have the formula for moment of inertia of a point mass. We know how to calculate moment of inertia for linear object, for ring kind of object, for disk kind of object. But right now we don't have the moment of inertia, formula for moment of inertia for hollow spheres. So to get the formula for this hollow sphere, we have to cut this hollow sphere in some elements. And obviously when we are cutting it into the elements, those elements should be either the linear one like rod, or it should be circular one like disc or ring, so that we can apply the formulas, or it has to be the point element so that we can apply the mr square formula. Okay, so here little bit understanding, little bit thinking about this. If we think about this hollow sphere, we have a thing. The thing is, this is the center for this hollow sphere, and obviously, you see, if I move at a distance x, and x is a variable, so if by moving at a distance x, we cut the hollow sphere through the plane. So by moving the x, I'm cutting the hollow sphere by a plane. Then I'm moving further by dx, and one more time, I'm cutting this. So I'm moving further dx, and one more time, I'm cutting this hollow sphere. So between these two planes, I'm having my element. And if you think about this element, if you think about, this element will be a circular element. It will be like a ring kind of element. And we know the moment of inertia for ring kind of element. And now see, this moment of inertia for the hollow sphere, we are calculating about the diameter. And this diameter for this, when you think about this element, which is a circular ring kind of element, this diameter will pass through the center of that element and perpendicular to that plane. Okay, so let's cut this element, and if we bring this element out, we'll be having a ring of obviously mass dm, and the radius of this ring, obviously here we have to calculate the radius. This will be the radius of the ring. I'm calling it small r. This whole radius is capital R because that's the radius of this hollow sphere, and we have moved by distance x. One more thing we can do, you see, if I join these 2 points of the element and if I calculate the angle, so I can convert the x into the theta also. So if this is the theta I'm defining, if this is the theta I'm defining, this is the theta I'm defining, in that case, you see, this radius, the formula for radius I can make as, if this is the theta, this is also the theta. So this, you see, this is a right angle triangle, this is the base, and this is the hypotenuse. So in that case, in that triangle, if you see, small r upon capital R will be equals to cos theta, or we can say small r will be equals to capital R cos theta. And one more thing you can see, this is equation 1, we can call, the x upon capital R is sin theta. And from here you can see, x is capital R sin theta. If we differentiate this equation, not with respect to anything, just differentiate this equation, then it will be dx, and r differentiation is nothing because it's a constant, r times of differentiation of sin theta is a cos theta, then it is d theta. So this is the relationship we are getting between the dx element and the d theta as a variable. So this is the relationship between the dx as a variable and the d theta as a variable. Okay. Now we need to calculate the mass, this radius we have calculated, r, we get the relationship here. Now to calculate the mass, I need this thickness. Okay, so this thickness, you see, this width is d theta, and this is the radius r. So this thickness will be equals to r d theta. Okay, so this is my element. Element is my circular element, and for this element, this circular element, the thickness is r d theta. Now we have to calculate the areal density so that we can calculate the mass of this element. Now to define the areal density, you can see the mass for this hollow sphere is confined over to the cross-section area. Since it is confined over to the cross-section area, we will be interested in calculating the areal density. So areal density sigma for this hollow sphere will be defined as the total mass, which is capital M, divided by the total cross-section area, which is 4 pi capital R square. This is our areal density. Areal while defining the areal density, I have assumed this mass is uniformly distributed. That's the first assumption I am taking, meaning uniform distribution of mass I am assuming. Uniform distribution of mass. So if it is not uniform distribution of mass, from here itself we'll be changing the calculation. Sigma will be a little bit different, and that sigma will be taking it into account, not this one. Okay. So now, since we are assuming that uniform distribution of mass is there, I have calculated the mass per unit area. So with the help of mass per unit area, we'll be calculating the dm mass of the element. So you see, the dm mass will be equals to, mass of the element will be equals to cross-section area of the element divided by total area of the whole object multiplied with the total mass. Or we can say density, areal density multiplied with the area of the element. This is dA. Now to calculate the area of the element, what we can do, we can cut this element. And if we cut this element, this is a ring type of element. If we cut this element and if we elongate this element, you see, it will be like this. Because see, the outer side, this is the side, outer side, and this is the inner side. The outer side will be a little bit longer, and the inner side will be a little bit lesser. But this cross-section area, we see the difference. This thing we can neglect. If we neglect this thing, this element, after cutting the element and after elongating it, it look like it is a rectangle. And in case of rectangle, we know how to calculate the cross-section area. That is the length multiplied with the width. Here the width is r d theta. This width is r d theta. And the length is periphery. That is 2 pi r. So it is 2 pi, and that too small r, not capital R, because the small r is the radius for this ring. Okay, so we can put the values here. So it will be sigma into 2 pi small r multiplied with capital R into d theta. Now let's put the values of sigma. So dm will be equals to capital R, capital M upon 4 pi capital R square into 2 pi small r into capital R d theta. So this r and r cancels out. This 2 pi and this cancel out, there will be 2 here. So this dm will be equals to m by 2r into small r d theta. That becomes the mass of the element. Now as you can see, my element is a circular element. It's a ring type of element, and this axis about which we need to calculate the moment of inertia for the hollow sphere is passing through the center of this from here. And for this kind of body, we know the formula for moment of inertia. So whenever there is a ring, and when we need to calculate the moment of inertia of a ring about the axis which is perpendicular to the ring and passing through the center, like this one, the formula we define as, the formula is mr square. That's the formula. I is equals to mr square. This I is the moment of inertia for ring about this axis, which is perpendicular to the ring and passing through the center. Here this m is mass of the ring. And this capital R I'm taking, it's not the radius of this, it's the radius of the ring. Radius of ring. So that's the formula. Now if I use this same formula for the element, because my element is a ring shaped element. So for this ring shaped element, if I need to calculate the moment of inertia di, that will be equals to mass of the ring. In this case, it was m here in the formula, but in this case, it is dm. So it is dm into capital R square, which is the radius of the ring, which is not capital R in this case, which is small r in this case. So dm into r square. That will be the moment of inertia. So let's put the values. So if I put the value, then it will be equals to m upon 2 capital R, small r, d theta. And in place of this small r, I can write this r cos theta whole square. And that will become m capital R, 1 and r from here will cancel out, by 2 r d theta cos square theta. There is one more r here. If we replace that one also, it will be mr square by 2 cos cube theta d theta. So this is the moment of inertia. This is the moment of inertia for my element, which is a ring shaped element. Okay. Now to calculate the total moment of inertia for this hollow sphere, we need to integrate this. So to calculate moment of inertia for the whole hollow sphere will be equals to integration of di, and we have to integrate it in such a manner so that the whole body should be covered. Okay, so let's integrate this. So it will be mr square by 2, we can take it out because it is a constant, and integration, there is a cos cube theta. This cos cube theta, I can write it as cos theta multiplied with cos square theta, and that cos square theta I can write it as 1 minus sin square theta. You see? So what I did here, this cos cube theta, I cut this cos cube theta into two things. One is cos theta and one is cos square theta. And this cos square theta I have written as 1 minus sin square theta because there is a relationship. Cos square theta plus sin square theta is 1. That's the identity. And the limit we have to put, and obviously if you can see here the limit has to be put in terms of theta. So if I want to convert, if I have to get the whole hollow sphere, this theta will be varying from minus pi by 2 to plus pi by 2. So limits will be from minus pi by 2 to positive pi by 2. Okay. So if you see this equation, in this equation we can use the method of substitution. So if I use method of substitution, in case of method of substitution, we substitute the variable. Here this theta I'll substitute by something else, and that something else is basically what I'll do, I'll write this sin theta as t. If I write as this sin theta as t, then I have to replace the d theta also. Then if you differentiate this value sin theta as t, if I differentiate this equation, it will be cos theta d theta is equals to dt. So if I substitute the variable, the new value for moment of inertia will be equals to mr square by 2 integration of, you see, this cos theta d theta. There is this cos theta d theta. This cos theta d theta I can write as dt. And this sin theta I can write it as t. So 1 minus t square in place of 1 minus sin square theta. And cos theta d theta I will be writing as dt. Okay. Now we have to replace the variable for the limits also, because limits are corresponding to the variable. So we have changed the variable from theta to t, so we have to change the limits also. So this is the equation. This is the equation defining the relationship between the two variables, theta and t. So from here we'll get the lower limit and the upper limit for the new variable. So if I put minus theta, minus pi by 2 in place of theta here, the value of t will be minus 1. So that will be the lower limit, no new lower limit. And when I put the value of theta as pi by 2, I'll get the plus 1, that is the upper limit for t. Okay, so this equation we have to integrate. So mr square by 2. If I integrate this equation, I'll be getting t minus t cube by 3, minus 1 to 1. So integration of 1 will be t, and integration of t square will be t cube by 3. Okay, so let's calculate the values. So mr square by 2, here we are having t minus 1 to 1, and minus times of t cube by 3 from minus 1 to 1. That will be equals to mr square by 2. So if you put the upper limit in place of t, that is 1, then minus of, we'll put the lower limit in place of t, that is minus 1, so minus minus will become positive, plus 1. Minus of, we'll put the upper limit, that is 1, it will be 1 by 3, minus of, we'll put the lower limit, that is minus 1 to the power cube, which is minus 1 again. So minus minus will be positive 1 by 3. So mr square by 2, 2 minus 2 by 3, that value will be equals to mr square by 2, 2 minus 2 by 3. That value will be 4 by 3. So if you multiply this value, the result you will be getting 2 by 3 mr square. That's the moment of inertia for hollow sphere about its diameter. Okay, so let's see one more time here. We wanted to calculate the moment of inertia for hollow sphere. This was the hollow sphere. And this hollow sphere, this moment of inertia we wanted to calculate about one of its diameter. Since we don't have the ready-made formula for that, we need to go for cutting the elements. So in this case, what we did, we cut the element, and that element was a ring-shaped element. Okay. So for this ring-shaped element, first we needed to calculate the mass of this ring-shaped element so that we can use the formula for moment of inertia for this ring. So if I want to use the formula, I need the mass of the element as well as the radius of the element. Radius we calculated here from this triangle. Radius of this ring we calculated from here using this triangle. And the mass we calculated using the areal density. And here we assume that areal density for this hollow sphere to be uniform everywhere. That was the assumption. If it is not, from here the whole calculation will change. Meaning calculation will remain same, the values will change. So wherever we are putting the sigma, that variable value of sigma will be putting. Okay. So after calculating the mass and the radius for my element, we put the values. Okay. We put the values and then we did the integration here. Because after calculating the moment of inertia for the element, then to calculate the moment of inertia for the whole body, you have to go for integrating it from the lower limit to the upper limit. So lower limit and upper limit was minus pi by 2 to pi by 2. And we got this relationship, cos theta multiplied with 1 minus sin square theta. Actually, it was cos cube theta. Okay. So we don't know the integration of that. So we use the method of substitution there. So in case of method of substitution, as you understand in the mathematics there, what we do, we change the variables. So here the variable was theta, so we wanted to change this variable by looking at the equation. So what we did, in place of sin theta, we put t. So in place of sin theta, if we are putting t, we have to replace the d theta also. So to get the d theta, we have differentiated this sin theta equation. So this was the value for dt we got. So then we replace the variable. Along with the variable, we replace the upper limit and lower limit also. And then after integration, we got this value 2 by 3 mr square, where m is mass of the hollow sphere and r is radius of the hollow sphere. Okay, so this is the moment of inertia for hollow sphere about its diameter. Now this diameter can be in any direction. It can be here, it can be here, it can be any diameter. Okay, so this is the formula. You can memorize this formula, and in future you can use this formula to get some different formulas. Okay, thank you.